Digital evidence is inherently volatile. A power surge, a misplaced keystroke, or a routine background process can overwrite timestamps or permanently destroy files. There is a persistent myth that digital investigations rely on a magic piece of software, that an investigator plugs in a device, clicks a button, and the program automatically surfaces the definitive proof. That is not how forensic science works. A poorly trained examiner equipped with a $50,000 enterprise software suite will consistently produce weak, easily dismantled conclusions. Conversely, a skilled examiner who understands underlying data structures can produce rock-solid, court-ready findings using entirely free open-source utilities. To extract truth from a hard drive or a mobile phone, we have to architect a legally defensible methodology from the ground up. This methodology requires three distinct layers: a highly controlled physical laboratory environment, a strict approach to selecting software tools, and an examiner with a deep understanding of how operating systems store and manage data. Legally defensible evidence is the product of a strictly controlled procedural pipeline. If the process is flawed, the evidence is worthless, regardless of the software used to find it. You cannot conduct a rigorous digital investigation on a standard office desk. The process requires a specialized, professionally managed space to prevent contamination and unauthorized access. Look at the layout of a proper digital forensics lab. Before any software is launched, physical evidence must pass through strict intake protocols. It moves into secure, lockable evidence cabinets, housed within a facility that mandates restricted entry and constant environmental controls. The computers inside this lab, the forensic workstations, are built to process massive data sets. Analyzing terabytes of data requires extensive RAM capacity, multi-core processors, and specialized interfaces capable of handling multiple distinct storage devices simultaneously. The physical design of the lab enforces procedural integrity. It guarantees that the chain of custody remains unbroken long before a single piece of software is ever opened. The first step in the actual digital workflow is preservation. To review a storage device without altering its contents, investigators use a hardware write blocker. This physical bridge allows the examiner's computer to read the data while mechanically preventing any signals from writing back to the original evidence. Once the device is isolated, the lab moves to acquisition. This is the process of capturing the preserved data and converting it into a forensically sound digital format. The target dictates the method. Pulling a physical disk image creates a static, bit-by-bit copy of a hard drive. Capturing volatile memory, or RAM, random access memory, requires extracting live data directly from a running system before the power is cut and the data disappears. To prove the acquisition was successful, the examiner generates a hash. A hash is a unique cryptographic string generated by an algorithm, functioning essentially as a digital fingerprint for a specific file or drive. If the hash of the original hard drive and the hash of the newly created digital copy match exactly, the investigator has absolute mathematical proof that the copy is a flawless duplicate of the original media. Flawless preservation and mathematical acquisition lock the digital state in time. This creates the immutable foundation required for admissibility in court. A verified digital copy is only raw data. Acquiring it is useless unless the investigator can parse and read the underlying structures. This brings us to examination. This is the mechanical process of inspecting the image's contents, navigating file systems, extracting metadata, or recovering deleted files. Examination extracts the artifact. Analysis gives it meaning. Analysis is the process of interpreting those extracted files, correlating them with network logs and timestamps, and reconstructing the actual sequence of user activity. Investigators rely on specialized software for both phases. These tools generally fall into two categories: commercial software suites and open-source utilities. Commercial tools like EnCase or Magnet Axiom provide professional support, streamlined interfaces, and integrated workflows. Open-source tools like Autopsy or Wireshark offer a high degree of transparency into exactly how data is being processed, greater flexibility, and significantly lower costs. Whether utilizing free command line utilities or expensive enterprise suites, the software only provides the data points. The human examiner must provide the context. Let's apply this pipeline to a practical incident. A university suspects a staff member of copying confidential exam papers to a personal device. Tool selection is an entirely strategic decision, dictated by the specific legal questions of the case and the physical storage media involved. The process begins at intake. The suspect's laptop and personal USB drive are physically secured, labeled, and logged onto chain of custody forms inside the lab. For acquisition, the examiner selects a hardware write blocker and a heavy-duty disk imaging tool to safely duplicate the laptop's entire hard drive without altering a single byte. Moving to examination, the investigator deploys a file system parser designed to read the specific internal directory structures of the extracted USB drive. For the targeted analysis, they select specialized registry tools to hunt through the Windows operating system, isolating the specific artifacts that record USB connection history and recent file access. Finally, for reporting, hashing utilities are used to mathematically prove that the recovered files on the thumb drive perfectly match the university's original exam documents. Proper tool selection is not a generic one-size-fits-all process. It is a highly targeted sequence of technical decisions designed to answer a specific investigative question. This structured approach prevents the single greatest flaw in modern digital investigations: tool dependency. Tool dependency manifests in several ways, but the most dangerous is the skill dependency trap. This occurs when an investigator learns how to navigate a software's user interface, but fails to understand the underlying data structures the software is processing. They become a button-click examiner. This leads directly to the black box problem. Many commercial forensic suites automate parsing and output a polished report without fully explaining the structural or mathematical steps used to reach those conclusions. That lack of transparency creates severe legal vulnerability. If opposing counsel asks an investigator how a specific piece of evidence was recovered, answering "because the software showed it" is exceptionally weak testimony that will be easily defeated. The required solution to tool dependency is cross-validation. A rigorous examiner will acquire an image using one piece of software, but verify its integrity using an entirely independent hash calculator. If an automated tool flags a registry timestamp, the examiner must be able to manually verify that timestamp against the raw registry code. You must depend on your methodology, not the software. Blindly trusting automated output is a liability. Cross-validating your findings is the only way to survive strict courtroom scrutiny. Look at the completed forensic architecture. Operating within a secure lab environment, evidence moves strictly from preservation to acquisition, through examination and analysis, culminating in reporting, with continuous cross-validation loops verifying every step. The software does not validate the findings. The human examiner does. True digital forensics is not a matter of buying the most expensive suite. It requires mastering the underlying data structures and utilizing software strictly as an instrument of a rigorous, mathematically defensible methodology.